The periodic law states that when elements are arranged in order of increasing atomic number, certain sets or properties will reoccur periodically. That's where we get the periodic table, is this repetition of properties periodically, which just means every, so many elements, there's a repeat. As you can see here, they kind of color-coded them. So like helium, this one, helium, neon, argon, all have similar properties. Lithium, sodium, potassium, all have similar properties, so on and so forth. So if we look at this repetition of properties and we look at where these elements are in the periodic table, you should probably start to notice something. That hydrogen one is kind of weird, so we're going to ignore that. But if we look at, say, the helium, neon, and argon, and we say, okay, those are green, which means they have properties that are similar, and then we look at where they are on the periodic table. Oh, helium, sorry. They're all in the same column. When we do the same thing with the lithium, the sodium, and the potassium, there's lithium, there's sodium, there's potassium. They're all in the same column. So this pattern emerges that when atoms are arranged by their atomic number, atoms that are in the same column, elements that are in the same column, have properties that are very similar to one another. The major divisions of the periodic table: metals, nonmetals, and metalloids, and you can see where each of these are on the periodic table. Nonmetals are in green, metals are kind of that beigey color, and then metalloids are purple. So metals are found to the left of the stairs. And so if I go back to here for 1 second, the stairs is this dark divisional line here. It starts at boron and then just goes down, stair steps down. And so that is what separates metals from nonmetals. Notice, however, there's always an exception to every rule in chemistry. Hydrogen here is a nonmetal, even though it's to the left of the stairs. Properties of metals are that they are shiny, they're usually solid at room temperature, they are good conductors of heat and electricity. Nonmetals are just the opposite of metals, so they are found to the right of the stairs, except, of course, hydrogen, who you'll notice throughout this class is always just kind of causing trouble, off doing its own thing, not really blending in with everybody else. Properties of nonmetals are just opposite of properties of metals. So properties of nonmetals is that they're poor conductors. If they are solid, not a lot of them are solid at room temperature, but if they are solid, they're dull, brittle solids. Like I said, not a lot of them are solid at room temperature. And then metalloids are touching the stairs. Are touching the stairs on either side, with the exception that aluminum is a metal. So if we go back to this slide for 1 second, aluminum it's right here, it is touching the stairs, but its properties place it firmly with the metals. Its properties do not match those of a metalloid, so aluminum is classified as a metal. And it has to be physically touching the stairs, so something like tin, which is kind of on the corner, touching the corner of the stairs, that is not a metalloid. It has to be touching on the left or the right. So metalloids' properties are just in between those of metals and nonmetals. They are sometimes called semiconductors. You've ever heard of semiconductors? That means they conduct electricity under certain conditions. Main group elements and transition elements are another way that we can categorize the elements on the periodic table. Main group elements are kind of where the periodic table is tall, so that's the yellow, and then transition elements are in the middle there. So the big distinction between main group elements and transition elements is that main group elements have a lot of patterns that we discuss and a lot of properties that repeat and things like that. Whereas in the transition elements, that kind of stuff falls apart a little bit. So the main group elements are kind of the normal ones that behave the way we want them to behave, and then the transition elements get a little crazy. Each column of the main group elements is a family or a group. They are called families because they have similar properties as we've already discussed. So you can see the family names here. We have the alkali metals are group 1, alkaline earth metals group 2. The halogens are group 17, noble gases are group 18. The lanthanide series is down at the bottom, the actinide series is down at the bottom, and you probably saw some of that yesterday in that P-table activity thing. And then, there's your transition elements and just other metals, other nonmetals. So the ones that you would need to know would be the alkali metals, alkaline earth, halogens, noble gases, those, and transition metals, I would probably say. Those are the family names that you should be aware of. So the alkali metals are group 1. They are very, very reactive. They react explosively with water, which I'll show you in just a second. And in fact, that reaction gets bigger as you go down a group. So lithium reacts pretty well with water. Sodium is a bigger reaction. Potassium is an even bigger reaction than that, down to cesium, where if you were to, there's like videos online, if you were to react cesium with water, you need to be in like a bomb suit. And then you can see on the picture here, we have lithium and sodium, just so you can kind of see what they look like. So this video loads. There we go. Here's the reactivity of these alkali metals.
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Let's zoom in real quick. Let's see if we can really get in there. So this side will reflect a lot of light. The other sides are pretty dull. You'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut. So for the potassium, this is the side that's freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those three, and I'm going to add them to water, and we can look at the kind of reactivity of those three alkali metals with water. So here I'm going to take the lithium, and add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here. And then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame, perhaps, or some sparks, or some shrapnel. And then the last one, I'm going to go ahead and put my 2 pieces of potassium in. That cut in half. So this is less potassium than the other two in terms of amount. You'll find that the reactivity is a little bit greater.
All right. Alkali and earth metals are group 2. They are fairly reactive, but they are not quite as reactive as the alkali metals. Halogens are kind of the opposite of the alkali metals. So they are extremely reactive nonmetals. There's 2 halogens there. So chlorine is kind of a yellowish gas. Iodine typically is a solid at room temperature. So I think it's like a purplish solid it's showing you there. And then the noble gases are group 18, the last group on the periodic table. They are extremely non-reactive. That's the property of the noble gases. So which term best applies to lead? If you find lead on your periodic table, it's number 82. So lead is a metal, and it's number 82, which means that it's out of the transition metals. It's just past the transition metals. So I would call it a main group element. Oops, why did that happen? Goodness gracious. I would call it a main group element and a metal. There it is. So as we already talked about, metals tend to lose electrons, which means they are going to form a positive ion or a cation. And nonmetals are going to gain electrons, which means that they are going to form a negative ion or an anion. And main group elements, this is one of the normal things that they do that transition elements absolutely do not, is that main group elements tend to form ions that have the same number of electrons as the nearest noble gas. So if I am trying to predict the charges of these ions, what I would do, so I find aluminum. Aluminum is atomic number 13. If we look at the noble gases that are kind of near aluminum, there's neon with atomic number 10, and there's argon with atomic number 18. Well, 13 is closer to 10, right? So what aluminum's going to do is it's going to form an ion, so it has the same amount of electrons as that neon. So to do that, it would have to lose 3 electrons, and so aluminum will form a positive 3 ion. Sulfur is atomic number 16, so we could go up to neon, which is number 10, or we could go to argon, which is number 18, which is obviously closer. So to get to 18 electrons, sulfur would need to gain 2, and so it would make a negative 2 charge. Nitrogen has atomic number 7, so it is closest to neon, because it would either be helium, which is number 2, or neon, which is number 10. So it's closest to neon. So to go from 7 to 10 electrons, it would need to gain 3, so it would be a negative 3. And then rubidium is atomic number 37. So it can either match krypton, which is atomic number 36, or it can match xenon, which is atomic number 54. 37 is obviously closer to 36. So to get to 36 electrons, rubidium would have to lose an electron and make a +1 charge. So within the main group elements, because of this pattern and the way that they form ions, there is a pattern to the charges of main group elements. So everything in group 1 makes a +1 charge. Everything in group 2 makes a +2 charge. Aluminum makes a +3 charge. And then we skip group 4. That's a whole other situation we're not getting into. Group 15 makes a -3, 16 makes a -2, 17 makes a -1, and then group 18 is your noble gases, so they don't make an ion at all. And I know these are labeled 1A, 2A, 3A, 4A, so on and so forth. That's just a different labeling method. So really it's group 1, 2, this would be 13, 14, 15, 16, 17, 18. Okay, so that's the pattern in ion charges that definitely would be good for you to know going forward. And that is it.